Alright, section 4.5 is the fundamental theorem of algebra. The fundamental theorem of algebra basically says that anytime you have a polynomial function with any given degree, you can write that polynomial as a product of linear factors as long as you're able to use the complex numbers. If we look at the fundamental theorem of algebra along with the number of zeros theorem, I'm going to write out what this means in plain English. Basically, the fundamental theorem of algebra with the number of zeros theorem means that anytime we have a polynomial function, it can be written as a product of linear factors where the number of factors will be equal to the degree of the polynomial. That's if we can take into account our complex zeros. Those are the imaginary numbers. In example 1, we're asked to use the figures to determine graphically the number of real zeros and the number of imaginary zeros. All zeros for the given polynomials are distinct. So here we have a third degree polynomial. How many real zeros do we have? And how many complex zeros then? Remember, the number of real zeros and complex zeros has to add up to the degree, so that means that we have two complex zeros. This graph doesn't cross the x-axis. Our real zero was right here where the graph crossed the x-axis. Since this one doesn't cross the x-axis and it's second degree, how many real zeros do we have? 0. We don't have any real zeros because the graph doesn't cross the x-axis. How many complex zeros do we have? We have 2. Here's a fourth degree polynomial. We know it's fourth degree, first of all, because we see it in the function, but also there's 3 turning points and our endpoints are going in the same direction. Remember, if your endpoints are going in the same direction, you have to have an even degree, and your degree will be at least the number of turning points plus 1. So we have 3 turning points here. That means that our degree is 4. How many real zeros do we have? We don't have any real zeros because this graph doesn't cross the x-axis. So how many complex zeros do we have? We have to have a total of 4 complex zeros because the fundamental theorem of algebra says that we have to have the same number of zeros as we have the degree in the polynomial. So since there's no real zeros, we have to have 4 complex zeros. Also, your complex zeros come in conjugate pairs. That's this conjugate zero theorem. So that means that if a plus bi is a zero of a polynomial, a minus bi is also a zero. Remember, conjugate pairs are numbers where the sign between the real and the imaginary part is different. In example 2, we're asked to find the complex zeros of this polynomial function if one of the zeros is negative I. Well, if negative I is a zero, what else is a zero? Positive I is also a zero, so I have 2 complex zeros plus or minus I. That means that those zeros could be written as factors, x plus I and x minus I. And if I FOIL this out, multiply your first terms together, that gives you x squared. Multiply your outside terms together, that gives you negative xi. Multiply your inside terms together, that gives you a positive xi. And multiply your last terms together, that gives us a negative I squared. What was I squared equal to? Negative 1. So a negative times a negative would be a positive 1. These middle terms are going to cancel each other out, and that means that this would be a factor of this polynomial function, x squared plus 1. Well, if x squared plus 1 is a factor of this fourth degree polynomial, I can divide that fourth degree polynomial by x squared plus 1 to reduce that down to a second degree polynomial that I can then factor or solve using the quadratic formula. So that's going to give us x squared plus 1 divided into x to the fourth plus x to the third plus 2x squared plus x plus 1. If you need to review long division, you need to watch the section 4.3 video where we went into great detail on how to divide polynomials. I'm going to go through this rather quickly. When we divide, we just divide the first term by the first term. X to the fourth divided by x squared is x squared. Then we multiply, and that's going to give us x squared, and then x squared times 1 is x squared, and then we need to subtract these terms. This one was x to the fourth. X squared times x squared is x to the fourth. X squared times 1 is x squared. We subtract these terms, and that's going to give us x cubed that I bring down, and 2x squared minus x squared is x squared. And then I can bring down that x as well. X cubed divided by x squared is x. So x times x squared is x cubed. X times 1 is x, and then we subtract these terms. and that's going to give us x squared, and then bring down the plus 1. And x squared plus 1 divided by x squared plus 1 is 1, and we can stop because when I subtract these terms, I get a remainder of 0. So I've got my factors now for this fourth degree polynomial. So this means that x to the fourth plus x cubed plus 2x squared plus x plus 1 is equal to, I get x squared plus 1 from my imaginary roots that I found over here, and I have x squared plus x plus 1. And now what I need to do is I need to factor this or solve this quadratic equation in order to find the other two complex zeros. So my complex zeros will come from solving this quadratic equation. So I need to solve this quadratic equation in order to find the other two complex zeros. Because they're complex zeros, I know this isn't going to factor. So how can I solve this? What are my choices? Completing the square or quadratic formula. Do y'all remember the quadratic formula? Right, this is the quadratic formula. Which do y'all want to use? The quadratic formula where a is 1, b is 1, and c is 1, or do you want to do completing the square? You prefer completing the square? What do y'all prefer? Completing the square? Alright, we'll use completing the square. So when I complete the square, I'm going to go ahead and subtract this 1 from both sides, and that's going to give me x squared plus x equals negative 1. Now I need to add a factor right here, and I add the same thing to both sides. And what I add is this middle term b over 2 squared. So I'm adding 1/2 squared to both sides, and 1/2 squared is 1/4. That means that this left-hand side is going to factor into x plus 1/2 squared equals negative 1 plus 1/4 is negative 3/4. How do I get that square off of this x term right here? Take the square root of both sides. What you do to one side, you have to do to the other, but what do you have to remember? You have to remember the plus or minus. So that's going to give us x plus 1/2 equals plus or minus. This is going to have an I because it's a negative number underneath the radical. The square root of 3 is the square root of 3, and the square root of 4 is 2. So x will be equal to negative 1/2 plus or minus I square roots of 3 over 2. If we look back at the original problem, it was a fourth degree polynomial. That means that I have 4 complex zeros. One of my zeros was given, that was negative I. So what's the other zero? Positive and negative I, and also negative 1/2 plus or minus I square roots of 3 over 2. These are my 4 zeros for this fourth degree polynomial. Now I could take these zeros and write them out as a factor, and I could write my polynomial as a product of linear factors where I may have depending on what my leading coefficient is, I may have a constant out front. I didn't ask you to write your complex roots out as factors, but I could have. On this problem, if I would have asked you to write out this polynomial with these complex roots, we would have written f of x equals x plus I times x minus I times x plus 1/2 plus I square roots of 3 over 2 times x plus 1/2 minus I square roots of 3 over 2. This is how I could write my polynomial function in example 2 as a product of linear factors like this polynomial equation with complex solutions indicates we can do. But I didn't ask you to do it on that problem, but you may see it on a homework problem. Question? No, they should both be a positive 1/2 because if I set this factor equal to 0, I need that 1/2 to be negative on both of these. The signs in between the 1/2 and the I term are opposite. That's why these signs are opposite, but this sign is going to be positive because that's a negative right there. Remember, when you write your zeros as factors, you change the sign in front of the number. Well, the sign in front of this number was negative, so this is why this is a positive here, and the signs in between the real part and the imaginary part are opposite. Good question. Alright, in example 3, we're asked to solve this polynomial equation. In order to solve this, I first have to set it equal to 0. So I'm going to move all of these terms over here to the other side so that my leading term is positive. So that's going to give me x cubed minus 3x squared plus 7x minus 21 equals 0. Do not forget the equals 0 part. If you do, you increase the chance of making a careless mistake and forgetting what you're doing. Whenever you have 4 terms in a polynomial, try factoring by grouping, because if it works, it's really easy, and that's what we're going to do here, is factoring by grouping. When you solve using factoring by grouping, you want to group your first 2 terms together, then the next 2 terms together with a plus in between. So that's going to give me x cubed minus 3x squared plus 7x minus 21 equals 0. If I would have had a negative 7 here, I would need to put a plus in between and put that negative inside the parentheses. Now we just factor a common factor out of each of these groupings. Out of the first grouping, what term do I have in common? I have an x squared in common. When I pull an x squared out of the x cubed, what am I left with? And when I pull an x squared out of this minus 3x squared, what am I left with? What term do I have in common between these 2 terms? A 7. When I pull a 7 out of the first term, what am I left with? And when I pull a 7 out of the next term, what am I left with? Now I have a total of 2 terms. Here's one term, here's another term. Terms are things that are multiplied together. Looking at these 2 terms, what do I have in common between the 2 terms? I have an x minus 3 in common between the 2 terms. When I pull an x minus 3 out of this, what am I left with? And when I pull an x minus 3 out of this, what am I left with? Now I have this factored, and then to solve it, I just set each factor equal to 0 and then solve for x. So that's going to give me x minus 3 equals 0 and x squared plus 7 equals 0. To solve this first one, I just need to add 3 to both sides, and that gives me x equals 3. Over here I need to subtract 7 from both sides, and that's going to give me x squared equals negative 7. How do I get the square off of the x? I take the square root of both sides, but I've got to remember to do the plus or minus. So that's going to give me x, because the square root of x squared is x, equals I square roots of 7, and don't forget the plus or minus. So my zeros here, the real and the imaginary ones, are going to be 3 and plus or minus I square roots of 7. These would be my zeros for this polynomial equation. In example 4, we're asked to find a cubic polynomial that's a 3rd degree for f of x with real coefficients where the leading coefficient is negative 2 and I have zeros of 1 and 2i. If my zeros are 1 and 2i, can you tell me what my third zero is going to be? Negative what? Not negative I. Negative 2i. That means that I can write my polynomial. In part A, I want to write this in the completely factored form. Well, in the completely factored form, I get f of x is equal to my leading coefficient, negative 2, times my factors that come from the zeros. I have a 0 at 1, so what is that factor going to be? X plus 1 or x minus 1? X minus 1. And then I have a 0 at 2i, so that factor is going to be x minus 2i. Complex roots come in conjugate pairs, so I also have a factor of x plus 2i. This is the completely factored form of this polynomial equation of degree 3, where I have an x cubed and I have this written as a product of linear factors. In part B, I'm asked to write this in expanded form. Expanded form just means you want to multiply everything out. So in part B, I get f of x is equal to negative 2 times x minus 1 times, and when I FOIL this out, that's going to give me x squared plus 2xi minus 2xi minus 4i squared. The I squared is negative 1. The minus 2xi and the plus 2xi are going to cancel each other out, so I could write this as negative 2 times x minus 1 times x squared plus 4. We're not done because I still have a binomial times a binomial here that I can FOIL out. So when I multiply this out, that's going to give me, when I multiply my first terms together, that's going to give me x cubed. When I multiply my outside terms together, that's going to give me plus 4x. When I multiply my inside terms together, I get minus x squared, and when I multiply my last terms together, I get negative 4. My last step then would be to distribute that negative 2 across, and I end up with f of x equals negative 2x cubed, we'll say plus 2x squared because I want to write these into descending power, minus 8x plus 8, and that would be the expanded form, and this would be the completely factored form. You need to pay attention to the instructions when you do your homework and see if they want you to write your answer in the completely factored form or the expanded form. If you can get the completely factored form, all you got to do is multiply and combine like terms to get the expanded form. This wraps up section 4.5.